sklearn, model selection, validation curve. Description. The validation curve function in scikit-learn is a tool for model selection and hyperparameter tuning. It systematically evaluates the performance of a machine learning model across a range of values for a specific hyperparameter while keeping other hyperparameters fixed. This process allows you to understand how the model's performance changes as you vary a hyperparameter and helps you identify the optimal value for that parameter. Inputs. Estimator: an instance of a scikit-learn estimator, e.g. decision tree classifier, random forest regressor. This is the machine learning model you want to evaluate. X. The training data features a NumPy array or pandas data frame. Y. The training data target labels a NumPy array or pandas series. Paramname: the name of the hyperparameter you want to explore. For example, max depth for a decision tree or C for a support vector machine. Paramrange: a sequence of values for the hyperparameter to be explored. You can use a range of integers, floats, or even a list of specific values. Scoring: the metric used to evaluate the model's performance. It can be a string representing a predefined metric, e.g. accuracy, precision, recall, F1, a custom function, or a list of metrics. CV: the cross-validation strategy to use. You can choose from different strategies like k-fold for k-fold cross-validation, stratified k-fold for stratified k-fold, shuffle split, or provide a custom generator. This determines how the data is split into training and validation sets for each iteration of the cross-validation process. Outputs. Train scores: a NumPy array containing the training scores for each hyperparameter value and each fold of the cross-validation. Each row corresponds to a hyperparameter value, and each column represents a fold. Test scores: a NumPy array containing the validation scores for each hyperparameter value and each fold of the cross-validation. Each row corresponds to a hyperparameter value, and each column represents a fold. Steps. Data preparation: the input data X, Y is split into training and validation sets based on the specified cross-validation strategy. Hyperparameter exploration: the function iterates through each value in the param range. For each value, it creates a copy of the estimator and sets the param name to the current value. Model training: the estimator is trained on the training data. Model evaluation: the trained model is then evaluated on the validation set using the specified scoring metric. Result storage: the training and validation scores are stored in the train scores and test scores arrays, respectively. Metrics. Accuracy: a measure of how often the model correctly predicts the class labels. Precision: a measure of how many of the predicted positive cases were actually positive. Recall: a measure of how many of the actual positive cases were correctly identified as positive. F1 score: a harmonic mean of precision and recall, providing a balanced measure of performance. Mean squared error: MSE used for regression tasks, measuring the average squared difference between the predicted and actual values. R squared: another metric for regression tasks, indicating the proportion of variance explained by the model. Visualization plots. Performance curve: the validation curve function typically produces a performance curve plotting the training and validation scores against the corresponding hyperparameter values. This curve helps visualize the model's performance trends and identify the optimal hyperparameter range. Error bars: to account for variations across the cross-validation folds. Error bars can be added to the performance curve, indicating the range of scores for each hyperparameter value. Fine-tune parameters. Hyperparameter range: choose a suitable range of values for the hyperparameter that covers the Potential optimal values. Start with a wider range and narrow it down based on the initial results. Cross-validation strategy. Select a cross-validation strategy that is appropriate for your data and the task. Consider factors like data size, class balance, and time constraints. Scoring metric. Choose a metric that aligns with your goals and priorities. For example, if you prioritize correctly identifying positive cases, you might use precision or recall as the scoring metric. Uncertainty methods. Error bars. The validation curve function often provides error bars or confidence intervals to represent the uncertainty in the performance estimates. This helps assess the reliability of the results. Standard deviation. You can calculate the standard deviation of the scores across different folds for each hyperparameter value to quantify the variation in performance. Challenges and fixes. Challenge 1. Overfitting. If the training scores are significantly higher than the validation scores, it indicates overfitting. The model is memorizing the training data and may not generalize well to unseen data. Sample use case. A decision tree with a very high max depth might perfectly classify all training data but perform poorly on unseen data. Fixes. Reduce the complexity of the model by adjusting hyperparameters like max depth, min sample split, etc. Consider using regularization techniques to penalize complex models. Employ cross-validation to assess the generalization ability of the model. Challenge 2. Underfitting. If the model consistently performs poorly on both the training and validation sets, it suggests underfitting. The model is too simple to capture the underlying patterns in the data. Sample use case. A linear regression model with a low number of features might fail to capture the nonlinear relationships in the data. Fixes. Add more features or increase the complexity of the model by using more expressive models like decision trees or support vector machines. Explore feature engineering techniques to create new features that better capture the relationships in the data. Ensure that the chosen hyperparameters are appropriate for the model and the data. Challenge 3. Data imbalance. If the dataset is imbalanced, e.g., more instances of one class than others, the model might favor the majority class and perform poorly on the minority class. Sample use case. The credit card fraud detection model trained on a dataset where fraud cases are much less frequent than non-fraud cases might struggle to identify actual fraud instances. Fixes. Use stratified cross-validation to ensure that the class distribution is maintained in the training and validation sets. Consider using different scoring metrics that are more suitable for imbalanced datasets, like F1 score or AUC. Explore oversampling techniques, e.g., smooth to artificially increase the number of instances in the minority class. Use undersampling techniques to reduce the number of instances in the majority class.